since we started this chapter, the first thing that we did was to try to understand limit from an intuitive, a graphical, and table perspective. But really quickly we realized that drawing a graph is not always an efficient way of evaluating a limit. So then continuity came into the picture. If a function is continuous, we can find the limit at any particular value of a just by doing a straight substitution. Wonderful. But then came other situations where the function is not continuous. If it's not continuous and we get a non-zero over zero, then we know that we have a vertical asymptote. So how do we evaluate the behavior around the vertical asymptote? We know that the answer will be infinity, but is it going to be positive or negative infinity? And we had mechanisms for doing that. Then came the other type of issues, such as limits, where when you do a direct substitution, you end up getting the indeterminate, 0 over 0, infinity over infinity. And you notice that it was not actually a tedious job to figure out that limit. All that we had to do was some sort of algebraic manipulation. Things would cancel out, and bang, we had the value of the limit. So all of these techniques are wonderful, and if we can apply them to a given function, they work just fine. There are functions, however, like trigonometric functions, where some of these algebraic techniques are not going to work. They will just not work. I will not be able to do some sort of factoring. I will not be able to rationalize the denominator. Some of these algebraic techniques are not going to work for certain functions. So therefore, how do we evaluate the limits of a unique group of functions, like functions that involve trigonometric expressions? So before we get to those type of functions, let's talk about a truly significant result of calculus. This is called the squeeze theorem. Informally, sometimes you're going to hear the sandwich theorem. But typically, the formal name of the theorem is squeeze, the squeeze theorem. Why the squeeze theorem? Actually, the name or the word squeeze is quite representative of what really happens here. So let me describe it. Imagine that you are given a function f of x, and you are asked to find the limit as x approaches c of f of x. And immediately, I know that our instinct has to be to see if f of x is continuous at c, because if it is continuous, a straight substitution will give us the limit. But let's pretend that things are tough. Let's say that no, f is discontinuous at c. And let's say that there is no algebraic manipulation we can tackle that will get rid of any indeterminacy or anything like that. Let's say that f of x is one of these unusual functions that do not follow any of the rules of algebra that we have so far. And there are, in other words, those functions exist, they're there. So what do we do? Well, this is where the squeeze theorem, if it works beautifully. The theorem says the following. Imagine that your function f of x, I'm going to go ahead and highlight it. Here is f of x. Your function f of x is such that is between u of x and L of x. U and L are two other functions that we are going to have to find. And we're going to have to show that f of x is between u and L. In other words, f of x is trapped, completely trapped between u of x and L of x in a neighborhood around C. So we only care about what happens in a neighborhood around C. Let me highlight the neighborhood. Here is the neighborhood. And what we have is that, and just look at the diagram, f of x is between the green graph and the blue graph. It is trapped between the two. And that happens around C. We don't care what happens far away from C. A limit is a neighborhood concept. So we are just focusing about what happens around C. And around C, F is trapped between U and L. Now, in addition to that, just being trapped is not enough. So I'm going to say and over here. There is something else here. We also have to have a squeezing effect. In other words, f of x not only has to be trapped by U and L, but it has to be squeezed between these two graphs. It has to be sandwiched between U and L. And you can see the squeezing. See how the green graph and the blue graph, they actually join each other over here. So all of the sudden, F remains in between, but around here, F is completely squeezed. It is trapped between U and L. And because of that, since around C, U and L are squeezing f of x, then that means that f of x will behave in the same way as U and L behave. In other words, if we know that the limit as x approaches C of U of x is equal to L, and we also know that the limit as x approaches C of L of x is equal to L, then the theorem will say that the function in the middle that is being squeezed, in other words, f of x, will also have the same limit as U and L. So therefore, the limit as x approaches C of f of x will have to be L as well, just like the limit of L of x and the limit of U of x. And that's not difficult to really see, right? If you notice again around C, all three functions collide together right here. Practically, it becomes one single piece over here. So around C, they all behave in the same manner. Let me show you a very short illustration of what happens through the squeezing effect by considering points on each graph. I want you to follow here. If you look at this animation, I would like you to follow these dots. There are dots on the red graph above, the red graph below, and the green graph. The green graph is being squeezed. Notice how all three dots are practically becoming one around zero. Boof, they collide. Here they come again from far apart. They're getting closer and closer because the green graph is being squeezed. Look at that behavior. All three dots getting closer and closer, snuggling themselves up nicely, boom, here they meet. So all three graphs have exactly the same limit at zero. So this is what the squeezing effect is doing. The squeezing effect is causing the function in the middle, the function that is squeezed, to behave in the same way as the outer two functions, as the functions that are doing the squeezing. One more time, and then we're going to go back. There it is. The dots are getting closer and closer together. As x is approaching zero, all three dots pretty much collide to one single point. What I want to do now is to formally state the squeeze theorem. I feel that it would be wrong in our parts if we just move on and not formally state such a crucial, such a fundamental result of calculus. So let's begin by stating the formal initial statement. It says here, suppose that u of x and L of x are two functions such that the following conditions are satisfied around x equals c. Again, let me go back over here and highlight a small neighborhood around c, emphasizing that a limit is a neighboring process. So around C, these are the two conditions that must be satisfied. Condition number 1, f of x has to be a function between u of x and between L of x. And sometimes this is the hard part of using the squeeze theorem. The fact that we have to find two functions, an outer and an inner, that are going to trap f of x. F of x has to be between u of x. Nobody says that u has to be the larger one, the function above. I can have it stated the other way around. So let me say, or u of x is less or equal than f of x less or equal than L of x. What we want to convey here is the information that f of x has to be between u and L, and we are responsible for finding u and L. And condition number 2, number 2, and I'm going to emphasize over here, and they both have to be together. Oops, I spelled add, not and. Okay, and it must be the case that the limit as x approaches c of L of x has to be equal to the limit as x approaches c of u of x. They have to be equal. Let's say that this limit is equal to L. And that's because of right here on the graph, it is showing big L as the value of the limit. So if this is the case, then this is the conclusion. Then the limit as x approaches c of f of x will also be equal to L. And this is the beautiful conclusion that will allow us to find the limit of the function. What I want to do now is to show you with an example how to put the squeeze theorem into practice. In example 1, they're asking us to find the limit as x approaches 0 of x squared times the sine of 1 over x. I want to emphasize that this is the function in question. Let me even write it here. We are dealing with f of x, and f of x is the product of x squared times the sine of 1 over x. And we are trying to investigate the limit of this function at x equals 0. Now, just by observing the function, I want you to notice how this function is discontinuous at x equals 0. And that happens because of sine of 1 over x. Sine of 1 over x is discontinuous at 0. X squared is continuous everywhere, but sine of 1 over x is discontinuous. I want to show you a picture of the graph of the function of sine of 1 over x. So here is sine of 1 over x, and I really want to emphasize that this is sine of 1 over x. This is not f of x. Our f of x includes this factor, is a product of x squared and sine of 1 over x. But I want to introduce you to the graph of sine of 1 over x. Look at this graph right here. This graph is oscillating back and forth between 1 and negative 1 around 0. Actually, in fact, it's oscillating throughout its domain. It keeps going back and forth between 1 and negative 1. And the same thing over here, back and forth between 1 and negative 1. But what is so interesting here is to see how dense the oscillation gets around 0. So dense that you just see a big green spot around 0. That is really showing how there is no limiting behavior. The graph is not converging to a unique y value. The graph just keeps going up and down, no matter how close x gets to 0. So pictorially, it's clear that sine of 1 over x has no limit at x equals 0. And also at x equals 0, there is going to even be a hole because 1 over x is undefined. However, our function f of x may actually have a limit at 0. And I should be able to find this limit using the squeeze theorem. And remember that the squeeze theorem doesn't require for f of x, the function that is trapped in the middle, that function that is trapped doesn't have to be continuous at x equals c. Continuity is not important here. This is about limits, and limits doesn't really care about whether the function is defined at c. In this case, c is 0. So then all that I have to do here is to be able to find the two outer functions, u of x and L of x. And then I have to show that the two conditions of the squeeze theorem are satisfied. And I want to guide you through that process. I want to show you how to find u and L, and then how to organize all of the conditions of the squeeze theorem. So let's begin. We want to start with an inequality that is universally true. Something that no one in the world can question you about. For example, we know that every sinusoid, every sine or cosine expression is always going to be between -1 and 1. So then I know that a good way to begin is to begin by saying that sine of 1 over x is between 1 and -1. No one can argue with you about that. That is always a great way to begin your analysis whenever you want to apply the squeeze theorem and trig functions are involved. This is a great way to start. Now, your function is x squared times sine of 1 over x. What I want is to have f of x here in the middle. Remember, in the squeeze theorem, f of x wants to be trapped by two outer functions. So one way to get f of x here is to multiply the middle part by x squared. But if I multiply the middle part by x squared, I have to multiply every other side of the inequality by x squared to keep balanced everything out. I need to balance my inequality. Otherwise, I will be changing things around and committing illegal operations. So, absolutely, I can multiply this middle part by x squared as long as I multiply the left part by x squared and the right part by x squared. Then I keep my inequality beautifully balanced. And if I do that, what I am going to have is negative x squared less or equal than x squared times the sine of 1 over x less or equal than x squared. And then I go, beautiful, because now this over here is my function. So now I can say that f of x is less or equal than x squared greater or equal than negative x squared. And this is now pretty much showing that I have found the two outer functions. I found the function in the bottom. Let's call this L of x. And I found the other function on top. Let's call this U of x. Again, though, please don't get all wrapped up about L. How do I know that this is L? L versus U, these are just names. It doesn't matter. You can call this one U of x. You can call this one L of x. The point is that you found your two outer functions. You found the functions that are trapping, or can we say trapping? Or that are enclosing f of x. Let's put it that way. So that's practically satisfying condition number one of the squeeze theorem. We found the outer functions. In other words, we found that L of x is going to be equal to negative x squared, and we found U of x to be equal to x squared. Fantastic. Now two, remember, just because you showed that this inequality is true, that f of x is between u and L, that's not enough. Now we have to show that condition number two is satisfied. We have to show that the limit of the outer functions exist and are identical. In other words, we have to calculate the limit of each u of x and L of x. So the limit as x approaches 0 of L of x is equal to the limit as x approaches 0 of negative x squared. This is equal to 0. Now we're going to show the same thing for the other function. The limit as x goes to 0 of u of x, this is equal to the limit as x goes to 0 of x squared, which is equal to 0. And this is great because what we showed here is that the limit as x goes to 0 of L of x is equal to the limit as x goes to 0 of u of x, which is equal to 0. So now, when you put conditions 1 and 2, again, condition 1 shows that our function is trapped by L and U. Condition 2 now shows that the limits of the outer functions as x approaches 0 exist, and those limits are identical. So with those two conditions, we can conclude, or we can say, therefore, by the squeeze theorem, the limit as x goes to 0 of f of x, the function in the middle, in this case x squared times sine of 1 over x, is going to exist and is going to have the same limit as u and L, which in both cases is the same, 0. What I want to do now is to show you a photo of our function f of x so that you really see how indeed it actually has a limit at 0. Here we have the sketch of f of x. F of x is really the graph in red in the middle right here. The outer functions are the parabola that opens up, x squared, and the parabola that opens down, negative x squared. And if you notice, this is exactly what we obtained here as we were working on step number 1 of the squeeze theorem. So we notice that f of x in the middle is trapped by these two parabolas. And what really happens is that not only is f of x trapped by the parabolas, but it's also being squeezed. And you can really see the squeezing effect, how here the parabola spreads very nicely up and down, and then it's being squeezed. It's just the oscillation gets very, very small, because around zero, it is really being pressured by the two parabolas. And that pressure, that squeezing effect, is causing f of x to have the same limit as the parabolas that open up and down. So this is exactly what is happening. The actual graph of f of x doesn't really include the parabolas. You could actually remove the parabolas, but by drawing the parabola, somehow you really see the entire theorem in action. Here we have example 2. They're asking us to find the value of this limit. I want to practice with another example how to apply the squeeze theorem. If you notice, this function right here is very similar to the previous one. There is some variation. I do see that we have an exponential, but x squared is still there, and sine of 1 over x is still there. Because of sine of 1 over x, this function right here is again discontinuous at 0. However, the process is very similar to the process of example 1. Number 1, we want to start with a result, an inequality, for example, that is always true, that nobody can question you about. So, for example, sine of 1 over x. We know that sine of 1 over x is less or equal than 1, greater or equal than negative 1. That we know for a fact. Then look at the inequality. In the middle, ideally, what you want is to have the function f of x. I don't have it yet. I only have sine of 1 over x. So let's build the function in the middle in stages. What would happen if I exponentiate every single side of the inequality? Exponentiating means I will be considering e to this expression, e to 1, and e to the negative 1. And I'm thinking of exponentiating because this is what I have here as part of my function. My function has e to the sine of 1 over x. Sine of 1 over x becomes the exponent. So if we do that, we are going to have, imagine, e to the negative 1, e to the sine of 1 over x, e to the 1. As long as I do it to every single side of the inequality and e to that number is defined, I am not doing anything illegal. Let me rewrite this nicely over here as e to the negative 1 is less or equal than e to the sine of 1 over x less or equal than e. Now, take a look. Do you have the function? No, you still don't have the function. What I'm missing here is x squared. Well, not a problem. Easy fixed. If I multiply every part of the inequality by x squared, I don't violate anything at all. And when I do that, let me rewrite what I have. I will get over here x squared over e less or equal than x squared times e to the sine of 1 over x less or equal than e times x squared. Immediately, I can now see my outer functions. This will be my L of x or U of x. Remember, these are just dummy names. This will be over here U of x. So what I notice is that I have found an upper bound and a lower bound for my function f of x. F of x, remember this is f of x. F of x now is between L of x and u of x. And this was condition number 1 of the squeeze theorem. Now, working on condition number 2, I have to figure out what is the limit as x goes to 0 of L and what is the limit as x goes to 0 of u. And hopefully they're going to end up being the same. If they are not the same, then I'm going to have to figure out another way to get u and L. So hopefully they will be the same. So the limit as x goes to 0 of L of x, this will be equal to the limit as x goes to 0 of x squared divided by e, which is going to be equal to 1 over e times the limit as x goes to 0 of x squared. And you know that the limit as x goes to 0 of x squared is going to be 0. So 1 over e times 0, that will be 0. Now, let's test the other limit. The limit as x goes to 0 of u of x. This will be equal to the limit as x goes to 0 of e times x squared. This is equal to e times the limit as x goes to 0 of x squared, which is going to be e times 0, 0. And all of a sudden, I'm so happy here because we found that the limit as x goes to 0 of L of x is equal to the limit as x goes to 0 of u of x. That limit is 0. So therefore, by the squeeze theorem, we conclude that the limit as x goes to 0 of the actual function x squared times e to the sine of 1 over x is going to be equal to 0 as well. How beautiful.